Alright guys, welcome back. This is our last topic here in Unit 11, 11.6, Functions as an Infinite Series. Would highly recommend that you've watched the summation video for the TI-84 graphing calculator uses before you watch this video, because we're going to be using a bunch of summation formulas in there. Some of it would just be writing, but also some of it will be evaluating. And if you haven't watched that video, you're going to just kind of miss how I'm getting the actual answer. So make sure you stop this, watch that, and come back. All right, so a power series in general. So we talked about an infinite geometric series where we had a1, and then each term after that was multiplied by r. So it'd be a1r, a1r squared, a1r cubed, and so on. We can write this as a summation. We discussed summations back in 11.1, so this is now just using our summation. But it's going to be an infinite summation because we're talking about an infinite geometric series. We're going from n equals 0 to infinity of an times x to the n power. So this is what's called a power series. So if we want to write these expressions as an infinite power series, they give us the expression 1 over 3 minus x. So we have to find that in terms of the 1 over 1 minus x, because we recognize that when we had a geometric series, 1 over 1 minus x is essentially what the geometric series representation is going to be for an infinite. So all we do is we think of this as 1 over 3 minus x equal to 1 over 1 minus u. And we use a u as like a dummy variable, not using x, otherwise it would get a little too confusing there. We're trying to solve for u. That's the whole goal, to be able to write our infinite series. So we cross multiply. Get 1 minus u equals 3 minus x. Subtract the 1. And then divide by the negative for the u, and we get x minus 2, if I just kind of flip it around. So that means that the power series written as an infinite series would be n equals 0 to infinity, that summation, of just x minus 2 to the nth power. That's our power series representation. Now, we also need to figure out where the series converges, because as we talked about with our geometric series that were infinite, it only converged when the absolute value of r was less than 1. Well, that's what this is right here. The absolute value of x minus 2 has to be less than 1. Well, in a case like this where it's a linear equation, we can say it's in between negative 1 and 1. Add the 2 over. And we can see this thing is going to converge from anywhere in between 1 and 3. Obviously, it can't equal 1 and 3 because it wouldn't converge when it's equal to. It has to be somewhere in between there. So when it's a linear expression like that, it's a very straightforward way of finding the convergence. Just put in between negative 1 and 1, solve the linear compound inequality. Now, if we have a squared term in there, it's going to get a little more interesting. The process of finding the power series doesn't change, so it'd still be what they give us, 3 minus 2x squared equal to 1 over 1 minus u. We cross multiply. 3 minus 3u equals 1 minus 2x squared. Negative 3u is a negative 2 minus 2x squared. And then u would be, if we divide by negative 3, we can cancel all the negatives, but the 3 doesn't do anything in terms of going into the 2, so we'll leave it as a fraction. 2 plus 2x squared all over 3. So our power series representation would be n equals 0 to infinity. Just knocked over my iPad if you heard a thud there. So it's 2 plus 2x squared over 3 to the nth power. Now for the convergence, because it's being squared, we can't work with the compound inequality in that same kind of way. We have to recognize what's happening is we would have the inside 2 plus 2x squared over 3 is less than 1, and then 2 plus 2x squared plus 3 is greater than negative 1. We have to solve two separate inequalities because of the x squared aspect of the problem. So we go ahead and multiply the 3 over. So we get 2 plus 2x squared less than 3. So we get 2x squared is less than 1. X squared is less than a half. And here's where it gets interesting, because when we take the square root of this, square roots, we have to have a positive and negative, plus or minus, which is going to flip the inequality signs here. So this is going to give us x squared. So x is going to be less than, it's in between a positive 1/2 and a negative square root of 1/2. And that's going to be our final answer there, because we're going to find on the other side there, if we work this out, we're going to get 2 plus 2x squared greater than negative 3. 2x squared is greater than negative 5. X squared is greater than negative 5/2. That's always true. Positive is always bigger than a negative there. So that's irrelevant in terms of the convergence, so we're only going to worry about converging between the negative square root of 1/2 and the positive square root of 1/2. We don't have to worry about rationalizing that. You can just kind of leave it in that format right there. So you're going to find that you kind of do need to set up the both, because depending upon the problem, it might not work for the less than one side. You might have to use the greater than negative one side. Pretty much comes down to what's the coefficient in front of x squared. If the coefficient in front of x squared is negative, you're going to have to use the greater than negative one side, because you have to divide that over and now flip the inequality sign. Whereas if it's a positive coefficient in front of x squared, then you just use the less than one side. But one of those will yield an x squared greater than a negative number, which is not relevant because that's always true, and then these things need to be limited to what they converge. So be careful with how you're setting that up. Now, the next couple things are going to be talking about different types of power series we can use to represent functions we've already seen. So e to the x, it turns out, and this was useful, this is pretty much what the calculator does when it calculates e to the power of x, when you use your calculator for this, is it's equal to the power series of x to the n over n factorial. And this will always converge no matter what x is. So this works no matter what, every single time. What we're going to do is we're going to find certain partial sums for these series rather than the infinite value, because that would just be using the calculator tool to e to the whatever power actually is. So if I want to find the fifth partial sum to approximate e to the 1.5, we're finding S5 here essentially. So what we're doing is to find S5, we need 5 of them. We need to do our power series always starting at 0, but then we go to 4. Because you'd have the 0, first, second, third, and fourth value there. So that would be based off of our 1.5. So it's 1.5 to the power of n over n factorial. And what we're going to do to evaluate this right here is I'm going to expand this out, and then we're going to use the calculator with the infinite sum to actually get our particular answer. So this would be 1.5 to the 0 over 0 factorial, and then plus 1.5 to the first over 1 factorial, and then 1.5 squared over 2 factorial, 1.5 cubed over 3 factorial, and then 1.5 to the fourth over 4 factorial. Those numbers, especially towards the end, are going to start getting very, very small, especially if e was ever less. It wasn't like e to the 1.5 was like e to like the 0.9 kind of thing. It's going to start getting very, very small there, doing the exponents and all those factorials. So we don't really want to do these individually. We want to go to this right here and then type this into our summation form in the calculator, the partial sum part right there. And you'll find that we're going to get e to the 1.5 is approximately in value of 4.398. So again, as I said in the beginning, if you have not watched the summation video in the calculator's video playlist, you need to go back and watch that. Otherwise, you're not going to know where I got that 4.398, because the exact answer of e to the 1.5 is 4.482. So it's pretty close. But obviously it would get even closer if we did a sixth partial sum, a seventh partial sum, and so on down the list. But again, fifth partial sum, n equals 0 to 4. If I wanted like an eighth partial sum, it would be n equals 0 to 7. And the way I'm asking for it in my class, I want you to write out the partial sums individually based off the summation, but then use your calculator to use the summation instead, rather than trying to calculate each of those individually. And that will make a lot more sense for these next power series right here, the trig series. Because for cosine and sine, it's significantly more complicated to write this out. We will still write out the expansion for it, but I do not want you typing that part into your calculator. That will get very, very, very tedious to attempt to do them individually in your calculator. You'll use the summation formula instead, just doing one nice step, where it's a little bit easier to set up. Very important to make sure you're careful. Cosine is the one where it's all n's, so -1 to the n, x to the 2n factorial, whereas sine has 2n plus 1 for the x exponent, and then 2n plus 1 for the factorial. So if we want to find the fifth partial sum of cosine of pi over 7, so cosine of pi over 7, we'd have the summation of n equals 0 to 4. Our cosine formula tells us it's going to be that -1 to the power of n, and then we're going to have the x value, the angle, pi over 7 to the power of 2n, all over 2n factorial. So that's what you're going to type into the calculator there. Again, we're going to set up the 5 partial sums. You'll see why you don't want to do the individual partial sums in the calculator. So we'd have -1 to the 0, pi over 7 to the 0, over 0 factorial. And then we're going to have -1 to the first, pi over 7 squared over 2 factorial, because it's 2n now. So you'll find that the exponent of the vector will be double what's the exponent for the negative 1. And then plus negative 1 squared, pi over 7 to the 4th power, over 4 factorial. And then negative 1 cubed, pi over 7 to the 6th power, over 6 factorial. And then negative 1 to the 4th, pi over 7 to the 8th power, over 8 factorial. So those are your 5 partial sums. Individually, much more annoying to type out those 5 different expressions to evaluate. So again, using your summation on your calculator, we're going to find that cosine of pi over 7 is approximately 0.901, using, again, the summation formula right there. And the exact value of cosine of pi over 7 is 0.90096, so it's pretty darn close to what we're going to get there with that summation. That's almost the exact same value. So again, you just have to be careful with typing into the expression. If you have to keep on watching that calculator video over and over to make sure you're comfortable with the overall process, that would be a good idea. I'll walk you through it step by step. And then the sine one, same idea is going to happen here. It's going to be a slightly different formula. So we have sine of pi over 12. We want to do the 5th partial sum, so it's our summation, n equals 0 to 4, negative 1 to the nth power, but now it's going to be pi over 12 to 2m plus 1, and over 2m plus 1 factorial. So we'd have negative 1 to the 0 power, and then pi over 2 to the 1st power over 1 factorial. So you're going to find actually, so the previous one, the exponent of the factorials were pretty much increasing even numbers, 0, 2, 4, 6, 8, and so on. These will now be increasing odd numbers because it's 2m plus 1. That's how we find an odd value. So then it's negative, so then plus, not equals, plus negative 1 to the 1st, pi over 2 cubed, pi over 12, those should have been pi over 12s there, and then 3 factorial, negative 1 squared, pi over 12 to the 5th, 5 factorial, negative 1 cubed, pi over 12 to the 7th over 7 factorial, and then negative 1 to the 4th, pi over 12 to the 9th over our 9 factorial. All right, so this is going to give us our partial sum value. So we're going to find our calculator right there. You're going to go through using the summation formula. So we should be getting 0.259. All right, so again, please use the calculator for that stuff. Don't try and do that kind of thing by hand. Well, by hand especially, but like individually typing into the calculator, that would just be very, very tedious. Use the summation formula right here. Type it all into one step. It's it's complicated as it is to type that out to make sure you get the correct answer, so just be careful. Now, kind of reviewing back to complex numbers, we talked about our polars. We have the exponential form of a complex number, which we kind of seen a little bit. You just recognize the cosine theta plus I sine theta. That was our cis theta expressions. So the exponential form of the complex number, r e to the I theta. So r is your, as usual, square root of a squared plus b squared. Theta is the tangent inverse of b over a, where we have to add on pi if a is negative. If a is not negative, we don't add on pi. So if I want to take this and write this as an exponential form of the complex number in terms of r e to the I theta, we find our r value first. So it's our square root of negative square root of 3 squared plus 1 squared. So we get 2 for r. Theta is our tangent inverse of b over a. A is negative, so we're adding on pi. This is essentially negative root 3 over 3 if it helps you recognize the value for the angle there, which would be a negative pi over 6. Plus pi is 5 pi over 6. So our complex number in this complex number in exponential form would be 2e to the 5 pi over 6 I. That's the equivalent way of writing that particular answer. So again, just be careful when you're trying to find your theta value, make sure you're properly adding on pi when a is negative, and then you properly remember your unit circle values. Final thing we can do with this stuff, interesting little factoid. So we know that we can't get a real number. We talk about logs of negative numbers, and that's why it's always been specified not real, not real, not real, implying you can get a imaginary complex number. So this works for the natural logs of a negative number. So ln of negative k just becomes ln of k plus I pi. So we just take the positive value inside there and just have a complex term I multiplying by pi. So ln of negative 5 would just be ln of 5 plus I pi. That's all it is. If you need to evaluate ln of 5, just type into your calculator. So then this would become a 1.609 plus I pi. Not always necessary to actually evaluate the ln of 5 or ln of whatever the number is. For the most part, they just want you just to rewrite it. That's all it is. You'll find that that will match to your exponential form if you actually went through the process of finding the value of r and then finding the value of theta, though obviously theta would not really match out too well in this particular case. But we could write it back into its complex exponential format, which would then be equivalent to the ln of negative 5, and that's where this came from. All right, so that's it for Unit 11. Only one more unit left in the pre-calculus curriculum as I have it. That's the stuff with vectors. So I'll see you guys next time with Unit 12 with the vectors.